So I'm very pleased to be here today ahead of the embargo. This will run as the paper is published to discuss deglaciation of northwestern Greenland during marine isotope stage 11. It's kind of a clunky title, but the meaning will come clear in a few minutes to anyone. Their significance pretty much wherever you live, particularly if you live on a coastline, but we all depend on coastlines. And we all are thinking a lot about global warming and the pace at which things can change. We have Paul Bierman at the University of Vermont, who's been a longtime contact for me as a journalist on the climate beat. I think I first quoted you in 2002 on a story on storminess, the history of storminess in the Northeast, which anyone reading headlines the last few weeks knows is highly relevant. Here, you worked in depth, literally, in Greenland with a remarkable trove of ice revealing past histories, ice and sediments. And we'll talk about that in a second. And Tammy Rittenour, who's at Utah State University and has come into she's one of the many co-authors here. Her work was helping to reveal the age of the things that were locked in that sample. So Paul, we'll start with you because just tell us a little bit about the question on the floor. What's the news here? Because again, the title could deter people who are thinking, oh, don't we know isn't Greenland like melting? So what is new and different? And then how did we get to this opportunity that this paper is built on?
Thanks, Andy. Yeah, so we know that Greenland's melting. That's pretty obvious from the news you watch, the satellites orbiting the island and telling us that it's losing weight and mass all the time. But what we've done here is different. We've picked up a core that was drilled in 1966, first ice core ever to get through a major ice sheet. And not only did they get through the ice sheet in 1966, they kept on going. And they went 12 feet into the sand and mud and gravel and cobbles and boulders that were beneath the ice sheet. They were frozen solid, something like minus 11 degrees Celsius at the bottom of the ice sheet there. And they would have kept drilling if they didn't blow out a bearing in their drill, which put an end to things. And so in July 2nd, 1966, they stopped drilling. They packed up the core. They brought it home. And it's a core that was, the ice part of it was studied a lot. And starting in 1969, but the bottom and the dirt, not so much. There are a couple papers. One looked at the pebbles, and another one looked at these small microorganisms called diatoms and inferred what the climate might or might not have done. And then it literally got forgotten and it vanished. In the mid-90s, the core, which had been at Krell in New Hampshire and then had gone to the University of Buffalo in their freezers, disappeared. Mm. The rest of the U.S. ice core collection went to Colorado. But the bottom of Camp Century, nobody knew where it went. And it wasn't until a couple of years ago when a woman named Dorte Dahl Jensen and I were sitting at a picnic table in Buffalo, and Dorte said, I've got some bits of old ice in our freezer that you might want to have a look at. And then the ball started rolling, and I was in Copenhagen the next year with a small group of people, and we held in our hands the bottom of Camp Century that I would say everyone in the ice core community thought was a goner. And the Danes had done an amazing job of preserving it in their freezers from the mid-90s up until now. So that got us started, but the location of the core is what's key. This isn't the edge of the Greenland ice sheet. This is 138 miles toward the center. Almost a mile of ice is there, elevation about 7,000 feet above sea level. And now we, as a community, have access to this 12 feet of sediment, and it's got all kinds of secrets stored in it. And those secrets include a frozen ecosystem from the past. It's of plant fossils, mosses, twigs, little midges, the things that fly around your head when you're in Greenland, all frozen solid. And now with the work that Tammy's done, which is the foundation for this particular paper, we know when the ice left. And the when, and one of the ways the first author loves to describe this, Drew Christ, is it's kind of a mystery novel. You're trying to solve the mystery. Mm-hmm. And we now know the when, we know the where piece of this, and we know what happened, which is that a mile of ice disappeared 400,000 years ago.
Right. And now that sounds like a very, very long time. And I remember conversations with editors at the New York Times when I was there saying, hey, there's a new paper on Greenland that says X. And there's this newsroom phenomenon called MeGo. It's my eyes glaze over, and it's something you see in editors' faces late in the afternoon when they're juggling a story, let's say about a president in trouble, and something about Ukraine, and something about this and that. And so this idea that Greenland was ice free and had midges and the like flying around, flitting around at that spot way up in the northern part of Greenland. How would you explain that to that editor to say, hey, this is actually really significant?
Yeah, so I would explain to that editor to think about what it takes to melt an ice cube a mile thick. That's a lot of warmth. And that ice cube holds a lot of water. In fact, if you melted the entire Greenland ice cube, if you want to think about it that way, global sea level would rise 7 meters, which is a better part of 25 feet.
Right.
So imagine where you live today if you're near the coast, and imagine that the tide just rose 25 feet. If that were a New York Times editor and they were walking around Manhattan, perhaps, the coastline would be completely different than what it was today. So it matters to everybody everywhere around the world if the Greenland ice sheet starts to melt, and a significant portion of it starts to melt, because not only are sea levels going to go up, we're going to reshape the geography of coastlines, but Greenland is bright white. Think about it as a giant reflector.
Right.
All the sunlight that hits the top of the ice sheet, it's bouncing back. It's not warming the planet.
Right.
Take that white reflector away, and Greenland becomes brown and green and soaks up that sunlight. So not only is Greenland storing water on land and keeping it out of the ocean, Greenland's helping to keep our climate cool by reflecting incoming sunlight. So for that editor, it matters if we lose the Greenland ice sheet.
There you go. So let's circle to Tammy on this question of the reliability of the dating and how that all works. So tell us about this method that was applied to get the precise dating and to understand the significance of all that living stuff that was in the bottom part of this core.
Yeah, so I was brought on to determine when that upper sediment underneath the ice sheet was exposed to light last. And I use a dating technique called luminescence dating that actually provides an age for the last time sand was exposed to light. So that was the premise. We had to collect these samples from the freezer in Copenhagen in the dark under red light conditions, and cut a little sample cube, no bigger than a domino, out of the middle of that core to be processed at my lab and determine how old it was when it was last exposed to light. The technique's been around for decades, but it's coming into its own in the last probably 20 years, where we've been able to apply it to older and older deposits. And it's unique in that radiocarbon, Paul describes there's midges and ferns and twigs in these sediments, but they're way beyond radiocarbon dating. So we've had to move to other dating methods to determine how old the sediments are.
So that's why that technique, which I think more people have heard about, isn't really.
Yes. We did try radiocarbon dating, and it was beyond the time range for radiocarbon. It took a while, and Paul kept asking me when the ages would be ready. But it immediately started pointing to something that was around 400,000 years old, which was surprising, in that we thought the Greenland originally 5 years ago, if someone asked, we would say the Greenland ice sheet formed 2.5 million years ago, when we start to see Earth's climate shifting to colder conditions. So having ages that come back around 400,000 years ago is quite recent and alarming. It means that the Greenland ice sheet is less stable than we expected.
And so when we went to do the dating, when Tammy called for the first time, and I think the original numbers were 396 or something was the first rough number off the machine, we just looked at each other and said, okay, we know when this happened. This is MIS 11. The interesting thing about MIS 11 is it's a very long-lived interglacial. So unlike our current interglacial, which we call the Holocene, which happens to be when modern civilization developed, this is probably not an accident that happened. We've been in this interglacial now about 10,000 years, 11,000 years. The MIS 11 interglacial lasted close to 30,000. So it's a long time, but the carbon dioxide levels looked very much like what ours did before the Industrial Revolution. They were between 280 and 290 parts per million. And if you go back and look, that's Civil War times, right?
Right.
And so we now are faced with this knowledge that Greenland's ice melted back substantially, and it did it in pre-industrial carbon dioxide levels. Not 450 ppm, not 1,000 ppm, but pre-industrial carbon dioxide levels. But it took a long time. It wasn't a quick melt.
Right.
So then fast forward to today, where we have increased carbon dioxide by a factor of 1.5. So now we're at 420, 421, 422. And unless we do something active, that carbon dioxide we've put in the atmosphere is not going away anytime soon. Yes, a lot of it's going into the ocean, but it's not going to disappear the minute you and I and Tammy stop driving our cars or running our oil heat or whatever we use. It's stuck there and slowly be soaked up by various parts of the Earth's system. That means we are creating a huge equivalent of MIS-11. We're creating a long, and we know that last time a long warm period took out Greenland, except this time it's a long warm period on steroids. We're seeing that heating. So if MIS-11 was 1 or 1.5 degrees Celsius warmer than pre-industrial revolution for us, we're there right now. I mean, if we look, we've already had more than 1 degree Celsius of warming, and with this sort of global heat wave that's going on right now, we're breaking records. Last week we broke records every day for the hottest day on record. Something like 8 of the 9 last years are the hottest on record. So it seems like there's you look at all this and you go, the last time it got this warm for a long time, the ice went away, and we're headed exactly down that path. It's kind of inescapable to me. I'm a geologist, so I tend to look in the past and for clues to the present and the future. It seems inevitable that we're going to have a warmer, wetter planet with higher sea level going forward, and that could be for a long, long time.
Right. Boy, oh boy, that's getting into the policy questions. There's one more aspect of the paper, and I want to get Tammy in on that, this idea of the significance as well in a minute. But I want to go back to one graphic from the paper, which was the modeling effort on sort of what would Greenland have been like if you, at that point when you saw that part of Greenland way up there in the Northwest, with these conditions. Can you talk about this part of the work?
Yeah, I need to shout out to Ben Kiesling, who did this work. Ben's University of Texas, Austin, early career scientist doing really cool modeling work of Greenland and ice sheets and sea level. So if you look at that green dot in the corner, that's Camp Century.
Right.
And what Ben did is said, okay, we don't know all the conditions around the MIS-11 warming and melting. So he threw the kitchen sink of model parameters at this. And he said, let's just look at the whole spectrum of ways in which the model could start up and the atmosphere could respond and all those things, and the ice sheet could respond. And he created a large suite of models. And then he said, okay, of all those models that I've thrown at this, I'm going to look at only those that allow Camp Century to deglaciate during MIS-11. That's the results you see in panel A here. And he then said, okay, of all those models, which one results in the least amount of sea level rise? That's the absolute minimum sea level rise. And when he does that, the smallest possible sea level rise that gets Camp Century clear of ice is 1.4 meters. That's about 5 feet. That's the minimum, but the takeaway is there are many other models that result in much greater amounts of sea level rise. All those models in the red and the yellow in figure A, that's a whole lot worse for us. They go up towards 6 meters of sea level rise. That's 20 feet. So it is possible that in MIS-11, Greenland accounted for a lot of the sea level rise. The total sea level rise around the world is between 6 and 13 meters. Ben's most extreme models would take 6 meters of that from Greenland. We don't know what the truth is, right? We need more Camp Century like holes punched all over the ice sheet, and then we can figure this out.
Those are pretty remarkable pictures of the planet at that last stage, again, with concentrations of carbon dioxide, again, lower than what they are today. But Tammy, when you step back from the luminescence work, that's that component of this, what do you think? How do you convey this work to folks who are not climatologists or even journalists? How do What sits in your mind?
Yeah, if this can happen naturally under natural conditions with slow changes in carbon dioxide that just naturally oscillate with the Earth planet orbital configurations, and then you speed that up and accelerate the CO2 input and increase it, you're looking at, like Paul said, you're supercharging the climate and making it much more likely that we're going to lose Greenland with in the upcoming decades to centuries.
Right. And, having stood on the top of that at the summit in 2004, and I was down by Kangerlussuaq in the southwest there the same year. It's a lot of ice. It's when I wrote my story for the Times, I did some pretty careful, still sort of back of the envelope, but fairly careful calculations. And the amount of water that's above sea level there is about the same as the volume of water in the Gulf of Mexico. So it's like if God came down and flash froze the Gulf of Mexico and plunked it up on land like a big fat pancake. That's the amount of water we're talking about. Hopefully, I was hoping at that time people would kind of get the picture. And I think we all, whether we're scientists or journalists, we're always constantly thinking how to convey something with enough meaning or resonance that people do something. And that gets back to what Paul and you were just saying. This is a huge deal. And we haven't talked about Antarctica. I guess, Paul, it sounds like the science is still early days on how, whether Greenland was dominant or Antarctica or other sources. But these are huge questions. And I've talked about this before. There was a paper that came out in 2016 by Clark and others that tried in a scientific way to say, well, the consequences of 21st century policy for multi-millennial climate and sea level change. And it really struck me. I love this graphic, which I kind of tweaked here a little bit, where you can see the Anthropocene and the Holocene. And these are just a tiny portion of your curves, the curve of marine isotopes. This is just a very recent time. And so today, the choices we have, whether we see them as choices, can take us to all kinds of levels of meters of sea level rise. But they're on these time scales that seem really tough. Tim Morton is a philosopher. Oh, that's good. Whatever you just did is a philosopher who he was written a lot on the idea of hyperobjects, things that are massively distributed in time and space relative to human experience, so that we really don't, fully grok them. And so I'm going to circle back to the policy question here with that in mind. If you're talking about this work really clearly showing that even in a less greenhouse heated climate, you can have many, many, many millennia with the Greenland as a very grassy, open place and sea levels many meters higher. Paul, before we were recording, you were talking about how this relates to things like the Paris Agreement and what we would even think of as success on climate change. When you see headlines these days, it's avoiding, it's these Paris tracks for emissions. Can you talk about what you think really needs to be absorbed by people?
Yeah, so I think the Clark diagram you put up there needs to be absorbed by people. That is probably the single most influential diagram in my last 5 years of sort of intellectual life. Was looking at that diagram and saying, that bulge of carbon we put in now is going to be with us for thousands to a few tens of thousands of years. And that's the sort of last piece of the logic that I've gone through with Camp Century, is that if that Clark paper is right, and if that modeling is correct, then we can't just stop with let's decarbonize, which we absolutely have to do. That there is no excuse for continuing to run a carbon economy. But even if that happens and we leave our current carbon dioxide levels at, let's say, even today, 423, we turn off the carbon spigot tomorrow, then it's going to take thousands of years for that level to fall significantly. And all that time, we are above the background levels that melted Greenland at MIS 11. Now, granted, the orbital configurations are different. I mean, this takes more than back of the envelope calculations, but the past is the clue to the future piece tells us that we're in trouble right now. What we're doing right now has water pouring off Greenland, the massive Greenland shrinking. You mentioned being at summit. It's rained at summit in the last couple of years.
Right.
And there have been melt layers, 4 or 5 melt events at summit since people have been there. If you look back in the ice core record, that should be once every couple hundred years. So things are changing all over the ice sheet, at the margins, at the summit. And so to me, yes, we have to do Paris. Yes, we have to decarbonize. But then we have to think about how do we remove carbon that's in the atmosphere. And I don't want to go down that fabled path of, oh, in 10 years, we'll have carbon capture and storage that'll be cheaper than water. You know, that's not the case. We can't live in that sort of vaporware fantasy of this will come in the future. But we really have to think about getting the carbon out of the atmosphere. And the first step in that is not putting any more in, for sure. So, you know, a lot of people will say, oh, we can't rely on carbon capture. But to me, it's a two-step thing where we have to decarbonize, and at the same time, we have to develop these technologies that in an economically and energy efficient way can scrub this carbon out of the atmosphere. And, you know, some of that is afforestation and reforestation. Put the trees back on, put the trees where they haven't been. Restorative agriculture that puts carbon back into soils. Those are all important. You know, the idea of carbon-based power plants where you grow switchgrass and you burn it and you capture the stack emissions and you generate the energy at the same time. I mean, there are innovative ways that we need to start thinking. And I am sure there are ways that none of us on this planet have thought about yet that some bright young engineer is going to come up with. Right. But unless we start going down that path, it just seems like we are going to get warmer and warmer and warmer. And we don't show any diminishment in our ability to pop carbon into the atmosphere. I mean, look at the Keeling curve. It's going up and up and up and up. It's not bending yet. So, you know, at least we got to start bending that curve. But to save Greenland, we got to do more than that.
It's a tough moment in human history. And there's a, you know, you've probably heard the term polycrisis, Adam Tooze and others in the economics. But there has to be a poly solutions approach. And that's where I see on the policy side, everyone ends up in these fights. They're sort of self-preservation fights, the smokestack stoppers versus the innovators versus, as opposed to, can we have an all of the above approach to this?
It's got to be an all hands
and Tammy
for this.
Yeah, Tammy, maybe you can unmute and offer your thoughts on that too. I'm sure you talked to your other colleagues there at the University of, you know, and elsewhere.
Yeah, and there are, so we can try to engineer our way out of it. The Earth has cycled, and we do know of natural pathways that we can try to enhance, try to sequester carbon beyond just this, like capturing it from a smokestack. You can work with the systems we have, the Earth systems, but we do have to play a role. We can no longer just throw the cards on the table and wait for nature to heal itself. We have done enough that we now need to play a stronger role in engineering our future and our way out of this. Because we, while civilization has grown during the current interglacial warmth, we as a species developed during the Ice Age. We are not adapted for this hothouse world that we're headed to. And we also are headed towards pathways that may not bring us back to a natural cycle again. And that's really important to consider, that you can actually kick the system out of its natural cycles and not get back to where we can have a habitable Earth for us and to feed our future generations.
Speaking of future generations, I wanted to see if I could finally get it to play. I think Peter's son worked out a little video summary of the paper. Here again, was talking about this new Science magazine paper, Deglaciation of Northwestern Greenland, basically showing that was an area that just 400,000 years ago had, they didn't have cows roaming, but it had open, dynamic landscapes that were ice-free. So let's see if this will work.
A new study in the journal Science shows that a mile of ice vanished from northwest Greenland about 400,000 years ago. That natural warming period can help us understand the effects of climate change today. Using frozen soil extracted in 1966 from beneath the modern Greenland ice sheet at a military base called Camp Century, an international team dated the loss of ice that drove global sea level up between 5 and 20 feet. Today, our atmosphere contains 50% more heat-trapping carbon dioxide than it did when Greenland's ice melted. As a result, Earth is warming quickly. July 2023 brought the 4 warmest days on Earth since record-keeping began. High temperatures melt ice sheets. Unless we stop emitting carbon and lower its concentration in the atmosphere, Greenland's behavior 400,000 years ago suggests a largely ice-free future for Earth, characterized by rising sea levels and oppressive heat. The ancient soil warns of trouble ahead.
I think that conveys pretty well to even my eyes glazed over editor what we're talking about here. And I hope that maybe, Tammy, if you have one more thought in mind in terms of what people can do with this knowledge too, that would be helpful.
Oh boy, what you can do. There's a lot of things that can be done, a lot of pathways that we can change what we're doing, the amount of carbon we're releasing, how we're treating the earth, and how we can help capture this carbon. But like Paul said, it's that engineering capability is not here yet. So the most that we can do is each play our own role in trying to reduce our carbon emissions and work towards a better use of fossil fuels and potentially remove fossil fuels from our energy budget.
And Paul, one of the things that I like about Wicked Problems is that there's something for everyone to do.
Exactly.
That there's, within that matrix there, from nature-based solutions to communication innovation to even the arts. I've had artists on here, and across the landscape, whether you're a physicist, an engineer, entrepreneur, you have a role, or a paleoclimatologist. Does that strike you as, do you think that did you see, well, you wake up in the morning doing stuff, right? You're doing your work. So you're not walking off into the wilderness and giving up.
No, I don't walk off into the wilderness. I do listen to NPR in the morning, but that's my morning.
I did a conversation on here a while back that was prompted by I've done several on sea level rise, but one was centered on a NOAA finding that while there's uncertainty around sea level rise through 2100, there's some pretty basic understanding of what's happening between now and 2050, which is within the lifetime of most politicians today, and something that, present day policy, whether at the village or national scale, can really grasp. And there was a young researcher working with Jeremy Bassis. He's in Michigan, but she's somewhere else now. She wrote a paper on connecting Main Street and ice sheets. That's very valuable. Because on the other end of this, of course, what you're also talking about is inevitable coastal change going forward for essentially centuries, that even with successful emissions mitigation. So having the conversations that get us attuned to these realities seems also a good start, because you can engage people on what's happening in their communities right now and then build toward this bigger picture. I don't know if that makes sense as well.
It does, but I think the greatest challenge we face right now is how do we make this not a partisan issue?
Yeah.
The glacier's not partisan, the sea level's not partisan, but our politics is partisan right now. And, I can only look back to when I was a child and the Clean Air Act and the Clean Water Act passed, and they passed under Republican administration with strong union support, because those plants that treated the sewage that used to foul our lakes were built by union labor. So what's changed? I mean, it seems to me that, somehow we have to unify at least the people of this country, but the people of the world, to realize that this matters to them, and then take action. And it's not red or blue climate change. It's just climate change.
So right. Thanks both of you for being here today. And good luck conveying this paper well beyond the media to citizens everywhere, and having everyone step back from the political dynamics. And I tried to do that years ago in a book I wrote with my wife in 2018 on the history of weather and climate knowledge. And when I thought deeply about this predicament I've been writing about since 1988, the real image of it that came into my head was that we're actually at a point where we're starting to change our understanding of our relationship with climate. That 99.99% of human history, climate system did stuff, and we reacted. We either died, moved, or innovated. And now there's a slow, grudging understanding that we're in a two-way relationship with the climate system. And it doesn't surprise me that that's hard for us, Republican or Democrat, to really absorb. And it's on a scale that's much bigger than, as you say, the Paris Agreement or, Biden policies. It's a bigger thing. We're at a very special juncture in Earth history and human history where we're really realizing how entwined those two histories are. And so thanks again for being here. Paul and Tammy, you can hang on, but I wanted to actually ask Paul, I wanted to record a few minutes with Paul on that 2002 paper. If you'd be
as long as you let me stand up for a minute and refill my water bottle.
Yeah. And Tammy, hold on, let me. This is his paleo paper in 2002 with Noren and Bierman, Noren, Steig, and others, and it's stuck in my head. I wrote about it in 2002, and it showed you that the kind of storminess we've had in the Northeast this past few weeks is not anomalous. It's just rare.
Yeah,
and sorry.
Yeah, I was just down the river from Paul at Amherst, at UMass Amherst, when that paper came out, finishing my master's on New England during the glaciation and El Nino influences at that time. And so, yeah, this paper, I guess it was 2002. I think my paper was 99, but it was definitely, we didn't know each other necessarily in person yet, but we were working on similar questions, different timescales.
Yeah, so this is a very different, subject than Greenland's history, but to me it reveals the deep importance of paleoclimate work. You can't really say something today in a headline or in a statement from an agency about something being unprecedented or even extreme without knowing the longer timescale picture. And Paul and Tammy, maybe you too, do you think people get this? Do people understand that? Yeah, like I use a slide. I say whenever you hear the word unprecedented, ask since when, as at least the starting point, whether you're a journalist or someone in a conversation. Is that kind of a fundamental need? Maybe Paul.
Yeah, no, I think the challenge here is that you're speaking to two geoscientists, and we've been trained in deep time and time thinking, and it's not on human time scales. But I've been thinking a lot about this paper. I mean, about once or twice a year, you ping me about this in some way.
I say, has it held up? And I haven't heard anyone say no.
No, I think it's held up. But something else has changed for me, especially after this last set of Vermont floods, and thinking about, okay, so we had floods this year. We had Irene. You probably remember we have this landscape change site with photographs back in Vermont. We have 70,000 photographs of Vermont in the past. And I Googled Montpelier flood in our website a couple of days ago. It's not Googled. I just put it into the search bar. And when you do that, you get floods in Montpelier starting in 1865. And you get them over and over and over. And it really started to make me question, is the problem here the fact that we have floods, or is the problem where we put our buildings and our people? These floods have come over and over and over here. And yes, climate change is making them worse. No question. It's making floods more frequent that used to be more rare. But many of these floods were happening before intensive climate change here in Vermont. Right. So I think that the real issue is not climate change here. The real issue is our traditional land use in the state, in New England overall, where this was a region settled based on water power, right?
Yeah.
And so where did people live? They lived near the water, and that's where the mills were, and that was the transportation corridors and all of that. And so, as we look forward, and you talked about the ideas of resilience and adaptation, maybe it's time to start thinking something which would be pretty sacrilegious, which is to say, at what point do we abandon the structure of our landscape right now that puts people and their homes and their businesses and their infrastructure in harm's way?
Right.
Or are we simply willing to pay the price in human suffering, potentially human lives, and in dollars to rebuild? I mean, you're showing images of the 27 flood in Vermont.
Right.
Far worse than what we just went through. Similar amounts of rain in parts of the state, but even a wetter ground. And it was in October and November when so much rain was falling. Flows in the river near us were 3 times higher in 27 than they were last week. But still, these homes are being rebuilt in the same places, and they're flooding in the same places. And so it's a real fundamental, unpopular, probably, statement to make of, should we leave the railroad tracks where they are, or do we pick them up and move them to higher ground?
Yeah. I hadn't thought of this until just now, but in a way, there's 2 paradoxes in the communication challenge. One was the one we were just describing, related to how do you get people to really engage with the far future and the far past in how we shape our plans for decarbonization. And the other is, how do we do that and also say community change is needed with or without climate change?
Right. But I had a really interesting discussion with a woman who's very high up in the historic preservation community in Vermont last week, and said, hey, from a preservationist point of view, what do you think about the idea of taking a historic home that's in or near the floodplain and picking it up and moving it, whether it's putting it up on stilts, whether it's moving it 50 feet up the hillside? And her view was like, we'd rather have the historic home, even if it's out of context, than lose it completely. Right. I'm sure there are people who would disagree with that, but it would mean a fundamental rethinking of many of our towns and villages to move them out of harm's way. But yet this is going to come up over and over along our coastlines around the world, right? We move lighthouses all the time. We don't think twice about moving a lighthouse, Cape Hatteras and all that, but to move an entire community,
that's so interesting.
Yeah.
And the kicker on your paper really made this point, by the way. Statistically, what was found here, you say the existence of natural variability in storminess confounds reliable detection of anthropogenic effects, meaning global warming going forward. During the past 600 years, New England storminess appears to have been increasing naturally. And then you conclude, detected increases in contemporary storminess may not be a reliable indicator of human-induced climate change. To me, this says, we got to decarbonize. We know that. In the meantime, these changes on the ground are essential if you want to mitigate losses.
Yeah, I mean, that statement in the paper is because if we look at the cyclicity, we should be on an upswing anyway.
Right.
But the other thing that really struck me about this, looking at these last storms, is the damage was so hit and miss. We live in Burlington, nothing. Parts of the mountains devastated, parts of the mountains not devastated. When we cored all those ponds all over New England, we'd find an event here, we'd find an event there. I think what it tells us is there is such a stochastic, random approach to who gets hit and when with all this. Yet we still, even with all that randomness, saw these patterns of increased storminess on this sort of 3,000-year cycle.
Right.
Back then. So that's nature's cycle, but we're messing with that whole thing right now.
Right.
Who knows if it holds. But anyway, my takeaway from this was, hard as it can be, it's the adaptation of getting these homes out of the danger zone or modifying the landscape in such a way that they're safer.
Yeah, and the same thing goes for wildfire areas and everything else I've been writing about. Tammy, any last thoughts on this paleo illumination and how it relates to messaging in the future?
Yeah, because it's if you're an archaeologist or an anthropologist and you've studied human history and civilizations, and you see when civilizations form and grow and become too big and too rigid, too sedentary, the cities are too locked in places. There's a cycle to the human history also, because we maybe start more hunter-gatherer and free to move around, and therefore we're easy to move. Things get unfavorable, things start flooding, houses, like the landscape starts changing, we move. We have now brought ourselves to the point where we're not mobile and not in that way anymore. We have social, political boundaries. There are people who are refugees in their own country because they can't leave because of rising sea levels, because of flooding, because of famine, because of war. And then all the social unrest is actually amplified by all the climate and environmental changes. So it's melting Greenland, rising sea level. All the mega cities in the world live within 3 meters of sea level, like most of the world's population, because that was our route to transport goods and to move around was by water. And so we've set ourselves up with our biggest cities and and then we've locked in political boundaries, and we've left populations to the point where they need to fight to get resources. So so while there's some kind of natural cycle, if we turn up the heat and have more energy in the system by trapping more of that energy, it drives bigger storms.
For sure.
And so it's all interrelated, just different timescales, different perspectives. But you talked about flooding and the word drought. Those are anthropogenic words. They're just part of a river goes through cycles.
Right.
Overtops its bank, and then it changes its river profile. It changes the channel width if it can. The word drought, that is a human response to reduced moisture. It's how we react to it or cannot react to it that causes the issues. And leads to suffering and leads to the greater impact of these climate events.